Okay, here's a video about the first part of Chapter 3, which has to do with truth tables, and you're going to look at 3 in those first 1 or 2 sections about negations, conjunctions, and disjunctions. Really, all a truth table is a mathematical way to take a statement. We give each piece of the statement, if it's a compound statement, a letter, usually P, Q, R, S, or T, and then we give it a truth value because something can either be true or false. And then when we look at putting them together and using a conjunction or a disjunction, what happens to the whole statement given the truth value of the individual statements. So for a truth table, we're going to put these guys together and kind of break them apart into each individual part, so that way it's a little bit easier to understand. And it's actually easier with P's and Q's than it is with the actual statement to talk about whether or not something is true or not. A negation is just a not. So if something, a statement P, is true, or if the statement P is false, the negation of that, using that little tilde, if it was true, a negation of a true statement would be a false statement, and the negation of a false statement is a true statement. So it's just a not. It just flips whatever's in your first column to your second column. When we have a compound statement that has P's and Q's, we have 4 different combinations of what could happen. So for the first case, my P could be true and the Q could be true. In the next case, P could be true, but now Q could be false. If P is false, Q could still be true, or they could both be false. And the way that this is set up, where P being true, true, false, false, and Q being true, false, true, false, that's how they're always pretty much going to start off. When you have a 2-piece one. Sometimes there's a different way that you can write these, but usually with a 2-statement truth table, the P is always true, true, false, false, and Q is always true, false, true, false. So when is a conjunction true? It is true when both of them, both P and Q, are true. So let's say you can retake the exam and you can turn in the lab late. So let P be, you can retake the exam, and Q being, you can turn the lab in late. When will this statement be completely true? Those are my 2 statements, so we're going to set up the truth table using the 4 possibilities. If P is true and Q is true, then my whole statement will be true. If P is true and Q is false, then my whole statement is going to be false, because I said you can do this and this, but then I'm not really going to let you do the second part. If P is false and Q is true, just like with the second possibility, I said that you could do both, and then I kind of went back on one, so the whole thing is false. And then, of course, if they're both false, then the compound statement is false. For conjunction, an and statement, this little upside down V means and, both of them have to be true. So for P and Q, for that compound statement to be true, both pieces, both P and Q, have to be true. So that first case is the only one that's ever going to be true, and the next 3 are going to be false. A disjunction is an or statement. So you could do the homework or you could do the lab. So in this case, let's P be, you do the homework quiz, and Q, you can do the lab. It's true if you can do one or the other, right? Because I said, well, you can do either this or that. So if P is Q and Q is true, then P or Q is going to be true because you had to choose from one. If P is true and Q is false, that's still okay because you can still do this homework quiz. And if now you can't do the homework quiz, but you can only do the lab, then P or Q is true. But if you can't really do either of them, and I said you could, then the whole statement is false. For a disjunction, your P or Q statement is going to be true when at least one of the individual statements is true. So if they're both true, it's true. If one is true and one is false, they're going to be true. But if they're both false, they're false. Much like with your set Venn diagrams, ands make things more restrictive. You have less choices with an and because there's more parameters that have to be filled. I have to have this, I have to have this, I have to have that. And so when you have ands, it becomes harder to find what you're looking for. With ors, it could be, it opens up more possibilities, so you're going to have more truths. We're going to look at a few of just ands and ors where you just have one symbol. It's going to get a little bit more involved later on. So let's look at not P or Q. So when you set up these, this is how my math lab likes it. It has a P, Q, a not P, the or statement in the middle, and then a Q. We're going to set up our first column and our second column with a true, true, false, false, true, false, true, false. And then to look at the big statement, I'm going to need a not P. A not P just flips the original P column. So now it's going to be false, false, true, true. And now what my math lab does, which is kind of odd, is that it will redo that Q column even though it's already right over here. And it puts the answer to the compound statement in the middle. So this is an or statement. An or statement is true when at least one is true. So I have a false and a true. That's going to be a true. A false or a false is a false. A true or a true is true. And a true or a false is true. For an or statement, you need at least one to be true. So this is the answer statement. This is the answer that you're looking for that overall question. Now another way that you can write it is to just put it all in one, which is what I do, because I just think it looks a little more confusing. I do put the not column in, but then I just compare these two, this or this, and that's a true. This or this is false. True or true is true, and true or false is false. Now notice I was starting from the P, not P, and going to the not Q. With ands and ors, you can look at them backwards, but later on when you're doing conditionals with arrows, it is going to matter the order that they pop up. So always start with the first one and end with the second one. This is just another way to write it. Either way is fine. Here's another example of a P and a not Q, which is going to be a different situation, because now an and is going to be more restrictive. Your first two columns are going to look the same. They're going to write that P column over again in my math lab. Now, you already have it there, so you could basically skip this part right here. The not Q just flips the Q column now. So it was true, false, it'll now be false, true, false, true. And for an and statement, I remember it's an and because like if you draw a little line through there, it makes an A, so it looks like, you know, the first letter for and. You need both of them to be true. And in this case, the first one's going to be false, and only the second one will be true, because I need two truths to make an and statement true, so only this one is true. Had this been an or, everybody but this third case would have been true. Well, let's look at when they're both negated. I have P and Q, not P and not Q. I've got to put those in. I got true, false, and true, true, false, false. Flip the first column for a false, true, false, true. Flip the second column for a false, true, false, true. And now an and statement is true when they're both true. So only this fourth one right there is going to be the true statement. They can get a little crazier, like if you have a whole bunch of symbols in between, in which case you're going to need to take care of the nots. And then look at the truth value for this first big statement. Look at the truth value of this statement, and then compare them. You're going to set it up pretty much the same way as before, because it's just P's and Q's. But now you're going to have this middle statement. That's going to be your final answer. So there's your first column. And we're going to look at this right here. And it's an or, so it's going to be true, true, false, true. So this is for that very first piece right in here, this guy right down here. Now we got to look at the second compound statement. which I have a not p, so it flips those p values, but the q's are going to stay the same now this time. This is an and, so the only way it's going to be true is if they're both true. So that third case right there, that's the only one that's going to be true. So now for your final answer, what you're going to do, and I'm going to try to write this over, is compare this column to this column. Because what you're looking for is what's this truth value statement and what's this big statement wedged together. So now I want true or false, true or false, true, false or true, true or false. Well, for an and, you only need one of them to be true. So in this case, let me see if I can get this to cooperate. I didn't think so. Sometimes that happens. I'm just going to have to put that back in. When you use two different programs, sometimes it gets upset with you. So now we're going to compare these two columns to get the final answer. So a true and a false is true. A true and a false is true. A false and a true is true. And a true and a false is true. And this is a very special type of truth table. When all of the scenarios in your final answer are true, it's called a tautology. When something is a tautology, that means something is always true. It's called a contradiction when it's always false. Eventually, you're going to have to do 3 cases. And I know this probably looks a little crazy, but your first column, I don't know if you remember. Let's see if I can go back and look. See how this was trues were grouped together and falses were grouped together? And then it was true, and then it alternated? Over here, my trues are still grouped together, but my falses are and still grouped together. But now I got an in-between where instead of going every other one, I got 2 trues, 2 falses. 2 trues, 2 falses. The reason why there's so many is because you got 2 options for P, and 2 options for Q, and 2 options for R. And when you say and in math, you're going to multiply. So 2 times 2 times 2, and that's how you get the 8. We won't do ones that have 4 because now then you would have 16 cases, and that kind of gets a little crazy. So here's a statement that using the 3, we're going to have a compound up front and a negation in the back. So it's going to get a little bit longer. Most of the time they'll give you these first 3 columns in here, and then you just have to fill in the rest. P and Q, nothing really going on there, so they just copy down. And this was, see that little or floating around out there? He's supposed to be in here. I don't know how he got over there. So an or statement is true when at least one is true. So these first 6 are actually going to be true. And then you're going to have the false down here. For this column, I need a not R. So all you're going to do is flip this not R column. So it was true, false, true, false, true, false, right? So now we're going to go false, true, false, true, false, true, true. For an, hey, where did you go? Okay. For an and, in the middle, we're going to compare these 2 groupings because it's the truth value for here and the truth value for here. So that and that gives you false, true, false, true, false, true, false, false. Because it's an and the only way it's true is when they're both true. Not sure why it keeps trying to get away from me. There. The other thing that you might see in this section has to do with all and nones, and these tend to be a little bit harder actually than the actual truth tables. And if you look at the 3.1 section, there's a little like diagram that shows you the opposites. All, no or none, some, at least one, half. Those are all different qualifiers that we're going to look at. When you negate these, it's probably not what you would think. The negation of some do is none do, not all. Because if I say some of the people in my house smoke. The opposite of that would not be all of them, because the sum just becomes the all. The opposite would be none. You just need to disprove one of them. For all do, you just need some do not, or at least one does not. If none do, then the opposite of that is just some do. You just need at least one person to not do that. And if at least one does, then none of them do. Some girls play soccer. So no girls play soccer. All boys are immature. Questionable. Not all boys are immature. Still questionable. I have a 19-year-old, so. Let's see. No students read books. Feels like that sometimes, but some students do read books. At least one person likes anchovies. No one likes anchovies. That would be the opposite. And that's your first few sections of truth tables. I know it's a little confusing in the beginning. If you just try to think about it in truths and falses and not what the actual statement is, it won't be as bad.